For my presentation, I chose to do Euler's formula, which is a beautiful formula from 3D geometry about polyhedra. I'm going to start this presentation off by explaining why I chose the topic. I'll then move in to what the formula actually means. What does it describe about 3D geometry and polyhedra? We'll then move into applications, and I'll run through some examples, and then straight into proof preliminaries, and then on to the proof. So if you spend any time online in math blogs or on Twitter, if you follow some mathematicians, occasionally they'll share a list of the most famous equations or their favorite equations. So this is a list by Ian Stewart, somebody I follow on Twitter, and he just shared a list of a bunch of famous equations. And you'll notice that equation number 6 is Euler's formula for polyhedra. I've never been in a class where I learned about the formula, so I just wanted to know why it's so famous. So I just wanted to take this opportunity to dive into the details and understand what the formula says and how it's proved. What does the formula mean? Well, here we have a collection, a random assortment of polyhedra, some famous ones. Here's the cube in the top right. And we'll notice that it has 8 vertexes, 12 edges, and 6 faces. Well, if you just follow the equation blindly and you add 8 to 6, vertexes plus faces, you get 14, minus off the edges 12, and you get 2. And that's not a coincidence. That's true for any convex polyhedra like the one shown here, which is a pretty astounding fact. Applications of Euler's formula. So this is a very simple example just to get us warmed up and to see the usefulness of the formula. So we're presented a polyhedra. We're told that it has 60 vertexes and 32 faces. And they want to know how many edges it has. So one way we could do this is count it, but you can imagine how awful that would be with such a complex shape. You would lose track, you might overcount and have to restart. You get an odd number, and you wonder why, you have to restart. So instead, we'll just plug it into Euler's formula because we have all the information we need. All we're missing is the edges. Plugging it into the formula is pretty straightforward. E, you solve for E, plug in V for 60, F for 32, minus 2, and you get 90. Moving on to a more challenging example. In this example, we're given a polyhedra, but we're not given any information. We have to deduce it all ourselves. We're just given a picture. So how do we attack this? We notice that every vertex is identical. And what I mean by identical is every vertex has a hexagon, 2 squares, and a triangle on it. So we could use that fact to get our edges as a function of vertexes and our faces as a function of vertexes. So let's start out with edges. So I have this picture with the numbers 1, 2, 3, and 4 on it. And that's this picture is trying to show that every vertex has 4 edges on it. So edges equals 4 times the vertexes. But every edge has 2 vertexes attached to it. So we have to divide by 2 to not overcount, which gives us E equals 2V. We need to do the same thing for the faces. Faces is a little bit more complicated. We're going to have to break it up to different cases. So F3 represents a triangle, F4 square, and F5 hexagon. Notice that if we add up all the squares, triangles, and hexagons, we'll have the total number of faces. So let's start with triangle. Notice that every vertex has 1 triangle attached to it, but every triangle has 3 vertexes. So V divided by 3 will give us the number of triangle faces. Moving on to squares. Notice that every vertex has 2 squares attached to it, but every square has 4 vertexes. So 2V divided by 4. Simplifying, we have half as many squares as we do vertexes. Finally, moving on to the hexagon. Every vertex has 1 hexagon, but every hexagon has 5 vertexes. So V divided by 5. So then we just plug that into our equation for F, and we get that F equals 31V over 30. Okay, so now this is where Euler's formula comes in. So we have v plus f minus e, just makes our substitutions because we know what e is in terms of v and we know what f is in terms of v. We simplify, we get v over 30 equals 2. Multiplying across, we get v equals 60. Well, we have e as a function of v, so we just plug 60 in for e of v, and that's 2 times 60, which is 120, so we have 120 edges, and the same thing for faces. 31 times 60 divided by 30 equals 62. Moving on to proof preliminaries, what we're going to need to know to dive into the proof for Euler's formula is something called Schlegel diagrams. And you could think of a Schlegel diagram as what something would look like if you took a picture of a polyhedra in front of one of the faces. So on the left we have the picture of somebody taking a picture, and on the right we have the Schlegel diagram, what it would look like. And you'll notice that it's nothing but a graph with some edges and some nodes. This is a very useful way of representing polyhedra. Schlegel diagrams are useful because they preserve relevant information about the polyhedra, and they're easy to look at. They're easy to see all the information in one place. So what do they preserve? They preserve the number of vertices, edges, and faces. They also preserve the number of vertices and edges per face, as well as the number of edges and faces meeting at each vertice. So how do we read Schlegel diagrams? Well, Schlegel diagrams is nothing more than a network graph. And you can think of the edge of this graph as the edge of the polyhedra, the node of the graph as the vertex of the polyhedra, and then the regions as the faces. So on the far right image, you'll notice the blue circle. That represents the face closest to the cameraman in the cameraman analogy. The yellow would be the one furthest away, and so on and so forth. We now have the tools necessary to start attacking the proof of Euler's formula. We're going to do it on a specific example, but it's going to be very easy to see that this generalizes very nicely to any polyhedra. So the polyhedra is on the right, and on the left is the graph representation of the polyhedra we're going to be using for the proof. We begin the proof by constructing a partial Schlegel diagram. We connect every vertice with an edge, but we make sure that while we're doing this, we don't enclose any regions, so we don't want to create any faces. And you'll notice that the first edge we create has 2 vertices. Then after that, every edge comes with an additional vertice until we get to the end. And so if we call all the edges at the end E1, then the vertices equals E1 plus 1, because at the start, we have one more vertice than edge, and then we just keep adding edges until we get all the vertices. We'll call this equation 1, and it will be useful later on. Now we're going to use our partially constructed Schlegel diagram and the remaining edges that we haven't filled in to try to figure out how many faces we have in terms of how many edges we haven't filled in. So what we need to notice is that starting from our partial Schlegel diagram, as soon as we add one more edge, we create a region. Remember, regions are like a one-to-one correspondence with faces. So every time we add an edge, we're adding a face. But we started out the Schlegel diagram with one face, the blue face. Then we add, we get another face, and we keep adding edges. We add up E2 edges. Every time we add an edge, we add a face. So faces equals E2 plus the initial face that we started with. So this is equation 2. And then we have equation 3, which is nothing more than noticing that the total edges was the edges from our initial partial Schlegel diagram plus the ones we just filled in to create the faces. We now have everything we need to complete our proof. All we need to do is create a linear combination of these equations to construct Euler's formula. So notice that we have V for equation 1, F for equation 2, and E for equation 3. So it might be natural to just add equation 1 and 2, V plus F, and then minus equation 3, E. And sure enough, when you do that, E1 and E2 cancel out, and you're left with V plus F minus E equals 2, aka Euler's formula. The only resource I used to create this presentation was Brilliant.com. That's where all the images come from and the animations. It's a great resource. I recommend you guys check it out if you want to learn more about 3D geometry or polyhedra or anything really. Brilliant's an excellent resource.